Okay, we're going to take a look at some square root word problems. So let's go ahead and start off by reading the problem. Special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. On Earth, the function f of x equals the square root of 64x approximates an object's downward velocity in feet per second as the object hits the ground after bouncing x feet in height. So here we have the function here, and it's going to represent the downward velocity in feet per second. So what's important here is that the velocity, the downward velocity, is going to be the function f, and x is going to represent the height that the object bounces after it hits the ground. It's always really important that we know what the variables mean when we read the problem. So again, the units here, downward velocity is in feet per second. And then the bouncing height is going to be in feet. Now this is the downward velocity of objects on Earth. Okay, well, we're talking about objects on the surface of Mars. So let's see what it says here. It says the corresponding function for Mars is compressed vertically. Remember, a vertical compression is your A value by a factor of about 3/5. Write a corresponding function g for Mars and use it to estimate how fast a bounce of 45 feet in height. So we're going to have to change this function. First, they tell us to label it g. It's going to be compressed vertically by a scale factor of 3/5. Everything else stays the same. Now all we have to do now is plug in 45 into our formula and then solve for g. Okay, so plugging this into our calculator, control divide to get the 3/5, square root 64 times 45. So here's our downward velocity, and we're going to go ahead and approximate it by rounding it to the nearest tenth. So 4.8 and don't forget the correct units, feet per second. Now, that same height, let's say if we did this on Earth, would the downward velocity be greater or less? What do you think? Without make a reasonable guess based on what you know and see if you can determine whether the downward velocity would be greater on Earth or less than on Mars. Okay, let's move along. I think you're going to be able to do number 2, no problem. Let's go down here and look at number 3. The diameter d in inches of a rope needed to lift a weight of W tons, so W is weight, units is tons, is given by this formula. How much weight can be lifted with a rope with a diameter of 1.5 inches? So we're going to plug 1.5 in for D, for diameter. Okay, and we're looking for how much weight. So in other words, we're going to be solving this equation for W. So to solve for W, remember we want to isolate the variable. So to isolate the variable, we have to get rid of this other stuff. So we're going to start by undoing the division here. So the inverse of divide is multiply. So we'll multiply by pi on both sides. So that will cancel out. So we have 1.5 pi equals the square root of 15W. And I think you should be able to solve that from there. Don't forget to put your answer in terms of weight and using the correct units. Okay, let's take a look at a graph problem, and I'll help you get started. So for number 4, the speed in miles per hour of a tsunami can be modeled by this function here. Notice we have a vertical stretch, where D is the average depth in feet of water over which the tsunami travels. Graph the function. Use the graph to predict the speed of a tsunami over water with a depth of 1,500 feet. So we have speed in miles per hour, and this is going to be our dependent variable, so that is going to go on the y-axis. Speed, and then we put the units here, miles per hour. Next, we're going to put the distance, our independent variable, or we should call this maybe depth, would probably be a better word. And this is going to be in feet. So now that we've labeled our dependent and our independent variables with the units, we're now going to have to set up a scale. So we're looking for the speed when the depth is 1,500 feet. So we know that we want to be able to find 1,500 feet on the x-axis. So if we start here at 0, and we want, let's see how many tick marks there are. 1, 2, 3, 6, 7. 25. So I could go by hundreds, but that would make these awfully close together. So I think what I'm going to do is I'm going to go by 500s, or better yet, let's go by 250s. So I'm going to go by 250. So 0, and I'm going to skip 1, 250, 500, 750, 1,000, 1,250, 1,500, 1,750, 2,000, okay, next I'm going to go ahead and plot some points here. So when x is 0, the speed, I'm going to make a table, input, output. So if I input 0, that would be 3.86 times the square root of 0, which would be 0. So that if the depth is 0, the speed is 0. So it's going to start right there. All right, so let's go to 250. So 250. Get out my handy dandy calculator here. 3.86 times the square root of 250. 61. So now at this point, I kind of have to figure out my scale here. So here my speed is going to be 61 miles per hour. So let's go up to the highest number I was going to go to, 2,000. Let's find out what that's going to be. 2,000. So I'm going to go up and copy this and change this to 2,000. So the speed's going to be 172.6. I'm going to go ahead and round that to 173 miles per hour. So from my lowest 0 to my highest 173, that gives me an idea that I might want to count this by maybe 20s. I'm going to skip every other one. Let's see, 20, 40, 60, 80, 100. Yeah, that should work. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. You know, we want to use as much of this window as we possibly can. Kind of stretch it out. So we know 0, 0. At 2,000, we're going to go up to 173, which is going to be approximately here. So we're going to go, we're not making a straight line. It's got to stretch, so it is going to be stretched. Let's find one in the middle. Let's go with 1,000. So 122. So 1,000, we're going to go up to 122. Right there. So what we want to do here is we just want to kind of sketch. Hopefully I do a good job. Curve through those points. Okay? Because what we really want to do here, it says use the graph to predict the speed. Now I might want to put another point here, but I think we're good. I'm going to go ahead and get a ruler out now, or get a straight edge. We want to know what the speed is when the depth is 1,500. So what I would do is I would go up from here up to the graph, and then go over to the speed from that point. So I'm going to predict, I don't want you to plug this into your calculator. I want you to make a prediction here. So going up 1,500 to the graph, going over, and so I'm going to predict about 157 miles per hour. So my prediction, and we're running out of time, so I'm just going to say is 157 miles per hour. See you guys in class tomorrow. Sorry it ended up being a long video. Hope you're having a good night.